use the chain rule to find dv dt, where we have v is the function x plus z divided by z minus y. X is equal to 3t, y is equal to 2t, and z is equal to 4t. Express the final answer in terms of the arbitrary parameter t. So, looking at our given function here, our function v, we see that v is a function of three variables, x, y, and z, and then each one of those variables is a function of t. So the chain rule tells us, the chain rule in R3 tells us that the derivative of v with respect to t, dv dt, is going to be equal to the partial derivative of the function with respect to x multiplied by the derivative of x with respect to t plus the partial derivative of v with respect to y multiplied by the derivative of y with respect to t plus the partial derivative of the function v with respect to z multiplied by the derivative of z with respect to t. So looking at this chain rule, we've got a lot of partial derivatives that we need to find. So that's where we'll get started. So we need to find all of the first order partial derivatives. So here we go. We'll start with the partial derivative of v with respect to x. Now, we'll keep in mind here, because we are differentiating with respect to x, that we're going to treat y and z as if they are constants. So let's keep in mind what our original function is. So again, we are given that v is equal to x plus z divided by z minus y. So since z and y are both constants here, we can treat this 1 over z minus y as if it's a scalar multiple. And then we're just differentiating with respect to x. So this is going to leave us with our constant multiple, 1 divided by z minus y, multiplied by the derivative of x, which is just 1. So this is equal to 1 all over z minus y. Beautiful! So now we're getting ready. We want to find the partial derivative of the function with respect to y. So again, we'll keep in mind here that in this case, we are differentiating with respect to y. So we're going to treat x and z like they're constants. So again, coming back up here to reference our given function, notice that y is in the denominator. So in order to differentiate this, let's rewrite this function by bringing the binomial of the denominator up to the numerator. So we can rewrite this as our scalar multiple, x plus z, multiplied by z minus y to the negative 1. So here we go, differentiating. We have, again, that scalar multiple that we just keep out in front. That's x plus z, multiplied by the derivative of z minus y to the negative 1. So this will be negative 1 multiplied by z minus y raised to the negative 2 multiplied by the derivative of y, which is minus 1. So this is leaving us with that scalar multiple x plus z, and in our denominator we're left with z minus y squared. Beautiful! And last but not least, we have the partial derivative of the function the function v with respect to z. So in this case, we are differentiating with respect to z, so we treat x and y like they're constants. So again, coming back up here to our given function, notice in this case that we have a z both in the numerator and in the denominator. So in order to differentiate this, we can either apply the quotient rule using this form, or we could apply the product rule using this second equivalent form. So the method you use for differentiation is up to you. I'm going to go ahead and differentiate by the quotient rule. So this leaves us with, we have the derivative of the numerator with respect to z is just 1, multiplied by that original denominator, minus the derivative of the denominator which is 1, multiplied by the original numerator, and this is all over your denominator squared, so z minus y squared. And let's simplify. We see that we have a negative here, so we'll distribute that through to both terms. And this leaves us with, we have z minus y minus x minus z, all divided by z minus y squared. So we can see those two z's cancel each other right out. And for our final answer, I'll pull that negative out as well. So we have minus y plus x, all divided by z minus y squared. Beautiful. So we have all of the partial derivatives. And so now what we want to go ahead and do is think about the parametric representations for x, y, and z in terms of t and differentiate those as well. So let's also keep in mind here that we have x is equal to 3t. We have that y is equal to 2t. And last but not least, we have z is equal to 4t. So differentiating these, we have the derivative of x with respect to t is 3. We have the derivative of y with respect to t is 2. And last but not least, we have the derivative of z with respect to t is equal to 4. And we're ready to go. We're ready to take these partial derivatives and apply the chain rule. So we have by the chain rule. And again, let's give ourselves just a little bit more room. So the partial or the derivative of z with respect to that arbitrary parameter t is going to be equal to the partial derivative of the function v with respect to x, so that's 1 by z minus y, multiplied by the derivative of x with respect to t, which is 3, plus the partial derivative of v with respect to y, so that was x plus z, all divided by z minus y squared, multiplied by the derivative of y with respect to t, so this is all multiplied by 2. And last but not least, this is plus the partial derivative of v with respect to z. And we have minus y plus x, all divided by z minus y squared. And this is multiplied by the derivative of z with respect to t, which is 4. So let's simplify this a little bit, get a common denominator. So simplifying, we can rewrite this as 3 times z minus y. And now I have z minus y here because I'm thinking about getting a common denominator. So I'm multiplying the numerator and denominator of this first term by z minus y. Then we have plus 2 multiplied by x plus z minus 4 multiplied by y plus x. And that is all divided by z minus y squared. And so before we go ahead and reparameterize this, let's simplify a little bit further. We can distribute each one of these constants through and then group up our like terms. So distributing those scalars through, we have 3z minus 3y plus 2x plus 2z minus 4y minus 4x, all divided by z minus y squared. And let's see, we've got lots of like terms here. We have 3z plus 2z, which leaves us with 5z in the numerator. We also have a minus 3y minus 4y, so we have minus 7y. And last but not least, we have 2x minus 4x for a minus 2x. And that's still all over z minus y squared. Alrighty, so we have simplified our chain rule, and now we're ready to take the original parametric representations of x, y, and z and plug them into our answer. So we're taking these and parametrizing our final answer here. So this leaves us with, we have 5 multiplied by 4t minus 7 multiplied by 2t minus 2 multiplied by 3t, all divided by, so z becomes 4t minus y is 2t squared. So what are we left with here? We have 20t minus 14t minus 6t all over 2t squared. And would you look at this, our numerator goes to 0. Everything cancels out, so we have 0 over 2t. This whole term goes to 0. So 0 divided by 2t just leaves us with that beautiful final answer of 0. So therefore, the derivative of the function v with respect to t equals 0. And that is our final answer.